our next topic is going to be deep Q learning. This is based on a Nature paper that was presented in 2015, and that was a seminal paper that was considered groundbreaking, and I'll explain why in a second. So first of all, let me just remind you of the deadly triad that we previously discussed, where the danger of instability and divergence in learning arises whenever we combine all of the following three elements. Number one, function approximation, right, which obviously we're going to use in deep Q learning. So a function approximation is a powerful, scalable way to generalize from a state space much larger than the memory and computational resources usually allows us to do. Bootstrapping learning, where we update targets that include existing estimates, as in dynamic programming or TD methods, rather than relying exclusively on actual rewards and complete returns, such as in the Monte Carlo approach. So bootstrapping is learning based on biased estimations, right? We use the estimation to compute target for fitting the following estimations. And then finally, off-policy training, where we're training on a distribution of transitions other than that produced by the target policy. Right? So we're trying to learn a target policy while behaving differently in the environment. And we previously discussed this deadly triad, where an algorithm possessing all of these three attributes is usually in more danger of instability and divergence in learning. However, the deep Q learning algorithm actually does combine all of these, and they presented various tricks to address learning instability, which we're going to discuss today. So the DQN algorithm is a deep RL algorithm, right? An RL algorithm that uses a deep neural network as a function approximator, right? So it uses function approximation, and it performs temporal difference learning. So we'll see a combination of all of these, which, as we just said, constitute the deadly triad, right? So we're in danger of learning instability. It's not straightforward to get this approach to work well. And indeed, in 2015, the team from DeepMinds presented the deep Q learning algorithm. This was the first deep learning algorithm to successfully learn control policies directly from high-dimensional sensory input using reinforcement learning, right, where the input is raw pixels and the output is action value function estimating the future rewards, which right, if we learn the optimal, the Q star values, it also implies the optimal policy. The algorithm is a convolutional neural network trained with a variant of Q learning. Okay, so we combine convolutional neural networks that are very good in processing images, right? So this will be, or they showed how this works well. They evaluated it on video game domains. And it was indeed able to suppress a human expert on various Atari video games. And this, for many people, represents the age of deep learning in reinforcement learning. Previous reinforcement learning models relied on handcrafted features combined with linear value functions. So we saw several RL algorithms that rely on linear approximators. The problem with these is that if you have very high level input data, such as pixels, you need a human expert, or you need some kind of an expert to define the relevant features, to extract the relevant features that will be fed into the linear approximator. But towards this paper, advances in deep learning have made it possible to automatically extract high-level features from raw sensory data, right? Specifically convolutional neural networks for images, for instance. So this is an example that we've seen previously, right? Just as a reminder, let's say that we discover through experience that this state is bad. In the tabular case, In naive Q-learning, tabular Q-learning, we know nothing about this state, just because it's a different state. And we also know nothing about this state that is very similar, but one dot is missing, one food pellet is missing at the top, so it's a different state. If we do tabular learning, we don't have any Q value affiliated with this state. Now you might say, oh, but we can just group together similar states, but then it results in a question of what is a similar state, right? And then you need an expert to define what are similar states, or how you'd like to group them together. So at the end of the day, we must generalize our knowledge. And again, this is an example that we've seen before, where naive Q-learning, after 50 training episodes, is unable to learn meaningful Q values, or Q values that imply a meaningful policy, because simply the state space is exponentially, right? It's Pac-Man position, the dots position, the ghost position, and after 50 training episodes, we simply didn't see or didn't encounter most of the states, and so, or maybe we encountered them once or twice, and we didn't try each one of the possible actions in each one of the states, so the Q values are not very meaningful. However, once we use a function approximator over some relevant low-level features, we can see that Pac-Man can learn very effectively even after just 50 episodes. Right, and of course, we can generalize this to larger map and do similar learning. Once we generalize our knowledge, we can even learn how to act in much larger state spaces, and we can still do this effectively. Right? We can generalize our knowledge, which results in efficient learning. For instance, it can learn very quickly that it should avoid the ghosts, and very quickly it learns to go towards the food pellets. So, what's the issues for generalizing our knowledge in reinforcement learning, unlike supervised learning? So initially the deep neural networks were used for supervised learning, and it's not necessarily straightforward how we can extend them to work well in reinforcement learning. Why is that? So in supervised learning, for supervised learning, we require a large amount of hand-labeled training data. But in reinforcement learning, on the other hand, we learn from scalar reward signals that is frequently sparse. We don't see it everywhere in our state space or at each step. So it's often sparse. It might be noisy. The rewards might be very noisy, and they might also be delayed. So you did some correct action, but you'll only see that the outcome later on, and you must affiliate it. You must understand that outcome is affiliated with some action you took a long time ago. So the labels become much more complicated in reinforcement learning. Another issue is that in supervised learning, we assume that the data samples are independent of each other, and that's very important. You cannot, it's very problematic to train a supervised learning model on correlated data. Again, we won't discuss that and the reasons in this course. You're more than welcome to take the machine learning course and dive deeper into the theory behind that requirement. But in any case, in reinforcement learning, one typically encounters sequences of highly correlated states, right? So I interact with the environment, and the state that I see at time step t and time step t plus 1 are highly correlated usually, right? So the states evolve over time. Finally, in supervised learning, we assume a fixed underlying distribution from which we sampled our data, our training data. But this is not the case in reinforcement learning, because the data distribution, the training data distribution, changes for control algorithms, right? So control algorithms, they update the policy that we're using to interact with the environment, which shifts the distribution of samples that we collect from the environment. And all of these are some issues encountered with trying to just apply or integrate deep learning with reinforcement learning. It's not a straightforward integration. And in that paper, in the Deep Q learning paper, the QN paper, they were actually the first to demonstrate that convolutional neural networks can overcome these challenges to learn successful control policies from raw video data in complex reinforcement learning environments. And today we're going to discuss what approaches they took in order to address these issues. So the Deep Q learning algorithms, the basic idea here is to train a generic neural network based agent that successfully learns to operate in many diverse domains. So we don't want to program or define as an agent that is able to learn on one video game but doesn't perform well in a different video game. So we want something more generic, a generic solution. The network is not provided with any domain-specific information or hand-designed features, so that's a main requirement, as I just said. So eventually it must learn from nothing but the raw input, the pixels, the reward, terminal signals, and the set of possible actions. So that's, we provide this to the algorithm, and then it should learn to operate in each one of the video games, of the Atari video games. And there are many video games, many different games, and they differ dramatically in the optimal policy, in how you should play each one of those, and we'll see several examples. So to start with, let's go back to the original Q-learning algorithm, and let's try to identify issues with simply integrating a deep neural networks with the simple Q-learning algorithm. Right, the Q-learning with estimations, of course. This is the deep neural network is an estimation. It is an approximation function for the Q values. And of course, previously we see, and you actually also implemented at home, simple Q-learning with function approximator. Okay, it's now, let's see if we can easily integrate a deep neural network instead of maybe a linear approximator that you implemented previously. Okay, so let's try to identify the problem with using deep neural networks in basic Q-learning. So as we just discussed a minute ago, first of all, we need to somehow address the correlated data samples, right, which can throw the deep neural network off while training. Very problematic for training deep neural networks. Next, we need to address the issue where we train on sparse data. That is, we only have a small portion of the state space or as training samples. So we have to still perform efficient learning on much sparser data compared to what's usually used to train deep neural network. And finally, we need to address the sample distribution shifts, where the training data comes from a non-stationary distribution, right? We update our Q values, that implies a different greedy policy, which shifts the training samples that are used to train our deep neural network, our deep Q network.